Welcome back to Terracotta Creation. In our previous episodes, we explored some of the most mind-boggling quantum concepts: superposition, entanglement, and wave-particle duality. We learned how particles can exist. We learned how particles can exist in multiple states at once, which is called superposition, remain connected across vast distances, which is called entanglement, and behave as both waves and particles depending on observation, which is called wave-particle duality. But what if we could harness these quantum effects for computation? That's where quantum algorithms come in. Terracotta Creation presents Quantum Algorithm, the Future of Computing. So, what is a quantum algorithm? A quantum algorithm is a step-by-step set of instructions designed specifically to take advantage of quantum mechanics, solving problems much faster than classical algorithms. While classical algorithms process data sequentially, one step at a time, quantum algorithms can evaluate multiple possibilities simultaneously because of superposition and entanglement. Imagine you're in a library looking for a book. A classical computer checks each shelf one by one. A quantum algorithm, on the other hand, spreads out across the entire library at once, instantly identifying the book you need. This efficiency is why quantum algorithms hold the key to revolutionizing computing. Now we will explore how do quantum algorithms work. Quantum algorithms are not just about having more powerful hardware. They require a fundamentally different way of coding and solving problems. So, how does a classical algorithm work? Classical computers follow a fixed sequence of operations. Each step depends on the previous step, meaning computations must be done in order. Think of a chef preparing a meal in a small kitchen. The chef has to chop vegetables, cook and plate the dish one step at a time. Quantum algorithms process multiple possibilities simultaneously. They use probability, superposition and entanglement to refine answers faster. Now imagine multiple chefs working together in a giant kitchen, preparing different parts of the meal at once. Instead of cooking step by step, everything happens in parallel, delivering the meal much faster. This parallelism is why quantum algorithms have the potential to solve problems exponentially faster than classical ones. So, where you can run quantum algorithms require specialized quantum computers, but even today's most powerful classical computers struggle to simulate them efficiently. Why can't we just simulate quantum algorithms on classical computers? Classical computers can simulate quantum states, but the required memory increases exponentially with the number of qubits. Adding just a few extra qubits makes it impossible for a classical system to handle the computation. Let me give you some examples of RAM requirements for quantum simulations to help you understand the key challenge. For 10 qubits, 10 KB RAM, which is easily simulated on classical machines. For 20 qubits, 1 MB RAM, still manageable. For 30 qubits, 1 GB RAM, still possible. For 40 qubits, 1 terabyte RAM, now it's extremely difficult. For 50 qubits, 1 petabyte RAM, it's nearly impossible. For 100 qubits, more memory than all the computers on Earth combined. This is why companies like IBM and Google are developing real quantum processors, because simulating quantum systems on classical computers becomes very challenging beyond 50 qubits. Why are quantum algorithms so powerful? Quantum algorithms can outperform classical ones in key areas. One of the most popular algorithm, Shor's algorithm or quantum cryptography, works in both types of computing. In classical method, factorizing large numbers takes thousands of years with this algorithm. But in quantum method, breaks any complex encryption in minutes. Another popular algorithm, Grover's algorithm, works in search optimization. In classical method, searching a database takes n steps with this algorithm. But in quantum method, finds the solution in root over n steps, exponentially reducing search time. Quantum simulations in drug discovery and AI also differ significantly. In classical method, simulating complex molecules is too computationally expensive. But in quantum method, accurately models molecular interactions, revolutionizing chemistry and medicine in less time. These algorithms hold the key to unlocking new technologies that are currently impossible with classical computing. Now we will explore the future of quantum algorithm, As quantum hardware improves, quantum algorithms will become essential for industries like AI, cybersecurity, finance, and scientific research. Quantum cloud computing is already here. Companies like IBM, Google, and Microsoft offer access to quantum processors for research and development. Hybrid quantum classical computing is emerging, where quantum computers solve specific tasks while classical computers process the rest. The next frontier is building large-scale, fault-tolerant quantum computers that can handle real-world applications. We are entering a new era where classical computing reaches its limits and quantum algorithms redefine what's possible. Are quantum algorithms just a more powerful way to compute, or are they unlocking a deeper understanding of the universe? Could quantum computing help us explore the fabric of reality, consciousness, and the fundamental nature of existence? Stay tuned as I explore deeper into the quantum revolution in future episodes. Let me know in the comments, how do you think quantum computing will change the world? And don't forget to like, share, and subscribe to Terracotta Creation. And also press the bell icon to stay entangled with our timeline. Thanks for watching.